Okay, so let's continue learning about waves. We'll call this waves part 2. So we just did anatomy of a wave, and now we're going to talk about how waves work with time. Okay, and we sort of have covered this a little bit, but let's just quickly lay down a wave and imagine it traveling along. Okay, there's the medium, and here's the wave. Okay, and it's going this way. Now, let's just talk about this particle and what it's done. So as this wave comes along, this particle has gone down, it's gone up, and it's come back down. And if the wave, continues to come, then this actually undergoes simple harmonic motion, right? Like we talked about a little bit earlier. Or it's a lot like if you were, say, looking down on a pendulum swinging back and forth. In fact, the mathematics works out roughly the same for both. We're not required to deeply cover the mathematics for this, but if you imagine the wave going by, you would see a very similar pattern to a pendulum oscillating. Something else that we can tie into this is what happens if a circle is spinning around. So there's also a tie-in to a circle here. So if we imagine, this point on the wave, which is, if we're looking at a pendulum down from the top, it'll also tie into circular motion here as well. So if we have a point on a circle, and that circle is spinning around and around, okay, like this, and you say have a straight rod connecting these two things together, you'll see that the green dot will always line up horizontally with the same point on a spinning circle. So there's a tie-in between waves traveling, oscillating pendulums, and a spinning circle. Okay, so we can use the same kind of terminology for all of them. One complete rotation of the circle is called a cycle. Okay, one complete oscillation of a pendulum can also be referred to as a cycle. And you can also talk about a wave in terms of cycles. Okay, so one oscillation equals one cycle. Okay, and then this brings in some terminology about how we time or talk about the rate at which cycles are happening. Okay, so the first thing we'll say is the period, and then we'll talk about frequency right after. So period equals the time for one cycle. Okay, so the circle spinning has a cycle, has a period. The wave has a period, and the pendulum has a period. All of them have a period. Okay, frequency is the inverse of period. So frequency is the number of waves per second. Continue. Okay, so I found a little animation of what we were looking for here, which is quite nice. Just sort of showing the relationship between circular motion and a sine wave. Okay, so if you've never seen that before, it's kind of neat. Notice we're kind of dealing in terms of radians. Okay, so in other words, one oscillation is equal to 2 pi radians, which may or may not come in helpful later in your life, but that's something to note. All right, so we're going to try to connect together a few things here. So we discussed the fact that what period and frequency are. So that leads to this concept. There's a relationship between frequency and period, right? Frequency and period. And that should kind of make sense when you think about it. If if t period is equal to seconds per wave, frequency is equal to waves per second, well, these are inverted fractions or ratios if you want, so then this relationship should be true. If that's true, then this should also be true. Okay? So there's your relationship. So for example, the wave has a period of 0.5 seconds, and remember we're in the MKS system, so everything's in seconds is our basic unit for time, so we deal with waves in terms of seconds. If a wave has a period of half a second, well then its frequency, if it takes half a second for one wave to go by, 2 waves should come by every second, right? So 2 waves, yeah, must go by every second. So then frequency equals 2. But the question is, 2 what? Well, 2 cycles, 2 oscillations, 2 repetitions per second. So 2 of whatever per second. Now there's a unit for per second. Do you know what it is? Young man in the front row, do you know what the unit for frequency is? No. It is the hertz, which is abbreviated Hz. Okay? So hertz is something happening per second. Okay? So if you're swinging on the swing, you might be swinging at 1 hertz, right? A 1 meter long pendulum, we learned yesterday or 2 days ago, has a period of 2 seconds. So its frequency would be half a hertz, and so on. Radio waves, which travel very fast, can have kilohertz or even megahertz frequencies, and so on. Okay, so there you go. Now we'll talk about the wave equation really quickly. There's another video just on the wave equation, but I'm going to write it here, and you can check out the other video for the explanation as to why this is true. Okay. If we're talking about electromagnetic radiation in a vacuum, you get a slightly different version of the wave equation, and that's instead of v, you have that specific velocity, which is c. C equals f lambda. We're going to use one example here, and yeah, I'll put a link to the wave equation video that explains where that comes from. Okay, so c equals f lambda. And so let's see if we can find a couple of numbers here. So let's say that gamma rays, a different color here. Gamma rays might have a wavelength equal to 1 times 10 to the negative 14 meters. Or shorter. And kind of on the other end of the spectrum, you might have, radio waves, like long wave radio waves that have wavelengths, up to 1 times 10 to the 4 meters or longer. That's a massive span. Right? That's 18 orders of magnitude from gamma waves to radio waves. So find frequencies at each end of the spectrum. Okay, and the way you're going to do that is you're going to rearrange this formula. And of course, C 3.0 times 10 to the 8 meters per second, roughly. It's slightly rounded, but. Okay, so solve that, and we're done. So just solving quickly here, right? You can solve with your exponents. 1 into here, 8 goes into 4. 8 subtract 4 is 4, so 3 times 10 to the 4 hertz. The difference between these two, 8 subtract negative 14 is 22. So here's kind of our range of frequencies in the electromagnetic spectrum from 30,000 hertz to whatever this comes out to be, a massive, huge, high number of hertz. Okay. Okay, let's think about that. So the question is the power of a wave. Right. It's an interesting question. So power is joules per second. So yeah, the power of a wave is related to its frequency and its amplitude. So higher amplitude means higher energy per wave pulse. Right, so yeah, so power has two kind of things to consider. You're right. Uh, that's correct. Absolutely. Um, yeah. So yeah, so each packet of wave energy, if you want to call it a packet, each wavelength carries an amount of energy related to its amplitude. It's not directly proportional. I have to relook up how it's related. Um, but anyway, it there's a relationship between the amount of energy and the amplitude of the wave, and then how fast the waves are coming with um, electromagnetic. It is set by the velocity, right? But there's more waves coming if they're shorter, and that ends up being overall more, if you want, energetic. Um, the problem here is, though, that there's another thing we're not really talking about, and that's photons. Um, so it gets a little bit confusing because electromagnetic radiation is considered to be like an oscillating electric field paired with a magnetic field, and they kind of oscillate. The fields oscillate at right angles to one another. They're not doing a good job drawing that, but we'll talk about that in another lesson. But it also behaves as particles of energy called photons, and we will maybe get into how you can connect the two. There's a Planck's equation that sort of tells you how much energy each photon will have based on the wavelength. Um, so I'm just thinking with amplitude, I don't know actually if amplitude plays a role or not. I'm not sure. I'll have to think about that because each photon is tied to um, the wavelength, right? It's E equals hf. So it's tied to frequency, but seeing as how velocity is set, um, it's also tied to wavelength, right? But sorry, I'm digressing. We'll just leave it at that for now.